All right, let's keep going. Let's do some more. So now I have my rod here. I've figured this out. I'm going to flip over the page. I'm going to sharpen up my pencil. I got these new Mitsubishi pencils, which are pretty awesome. I really like them, but they're very soft, so they run down really fast. I'm going to do the same thing I just did, but I'm going to do it around a different axis. And let's just see what happens. You don't need the parallel axis theorem. You can just calculate moments of inertia around any point just for fun. It just gets really tedious, and sometimes the integrals get a little too hard for us to do at this stage, but that's okay. If you like integrals, they're really fun, and someday, if you don't already, you will really like integrals. So let's say I want to do the same rod, M and L. M over L is lambda, all the same business, but I want to do it around a point here at the end. So I have my little masses. So distance x away, that's my dm, that's my dx wide. Okay, and I'm just going to integrate again. And so let's calculate my integral of r squared dm, which is going to be x squared dm. And this time my limits of integration are going to be from 0 to L. Now my dm is still going to be the same thing here. dm equals m over L dx, just like before. And so I can write this as the integral from 0 to L, m over L times x squared dx. That's just x squared times dm, which is equal to m over L x cubed, and then I'm evaluating that from 0 to L. Now you can already see how this is going to be, x cubed over 3. Evaluated from 0 to L. You can already see how this is going to be different. It really comes down to those limits of integration as to why the moment of inertia is different around the different axes. And so my moment of inertia I for a rod about the edge is equal to m 1/3 ml cubed over L, which is just 1/3 ml cubed. That's a 3. 1/3 ml cubed. Now that's not 1/12 ml squared, right? It's different. And so remember, this one was 1/12 ml squared. This one is 1/3 ml cubed. Sorry, 1/3. What did I just do? That was silly. Wait. Erase. Sorry. 1/3. It's not that different. 1/3 ml squared, not ml cubed. So it's similar. ml squared over 12, ml squared over 3. Notice the moment of inertia is bigger because more of the mass is further away from the rotation center, so it's more inertial. It's harder. When it's in the middle, you have more of the mass scooched up close to the rotation axis. It doesn't have to go as fast. When you're all the way down at the end, most of the mass is way out there, so it's going to be a lot harder to rotate. So let's show that this is the same as the parallel axis theorem. So if we remember, parallel axis theorem states that if I know the moment of inertia around the center of mass, which I do, it's 1/12 ml squared, and I want to translate that to a parallel axis some distance d away, and here my distance is L over 2 away. I should, that's going to be my moment of inertia around point O. It's just going to be I around the center of mass plus md squared, where d is this distance. So let's plug it in and just see what we get. I naught is going to be I center of mass 1/12 ml squared plus md squared, where d is L over 2. I don't know why I'm making that one lowercase. They're both uppercase. And so that's 1/12 ml squared plus ml squared over 4 times 3 times 3, which is over 12. 3 plus 1 equals 4 ml squared over 12, which is ml squared over 3, which is the same as what you get here. So this wasn't that hard to redo, but once you know it and you've done it once, why not just use the parallel axis theorem? It's super helpful. Okay, next video coming up.